In this video, I use a simple numerical example to introduce the RRK theory in chemical kinetics. The RRK theory assumes that the rate of a unimolecular reaction is proportional to the number of ways of distributing energy epsilon among the internal degrees of freedom of the reactant molecule in such a manner that the critical energy epsilon C is localized in one particular degree of freedom. I copied this paragraph from UPAC Gold Book. This is the web link that you can use. Now I'm going to explain this sentence. Over here, it's just we need to distribute a total amount of energy epsilon to all vibrational modes of the reactant molecule. In RRK theory, we assume every single vibrational mode has the same vibrational frequency. And then one of the vibration mode corresponds to the reaction. And if that particular vibration mode gets enough energy, epsilon C or more, then the reaction may occur. If that particular vibrational mode does not have enough energy, that means lower than epsilon C, then there's no reaction. Now I'm going to give you a more specific example. Let's say we have a triatomic molecule. That means 3 atoms. Assuming this molecule is nonlinear, then we have 3m minus 6. 3 vibrational modes. And again, in RRK theory, all 3 vibrational modes have the same vibrational frequency. I'm going to use Greek letter nu. Now let's say we distribute epsilon equals 3h nu. All right, we'll give 3h nu to the 3 vibrational modes. Okay, let's say A, B, 3. Okay, 3 different vibrational modes. And then when mode C gets 2 plus h nu, that means 2 or more h nu, the reaction occurs. All right, so how do we calculate the probability of the reaction proceeding with mode C getting 2 or more h nu? Well, all we need to do is we need to distribute this 3 energy quantum to the 3 vibrational modes, and we'll see how many arrangements are there. And then we look for the arrangements in which this mode C gets 2 or more h nu, right? So it sounds really abstract and boring. So I'm going to give you another problem here. I will just put 3x into 3 boxes. All right, box A, box B, and box C. All right, C is special. All right, if C gets 2 or more x, this box C will become a chicken. All right, it's magical. And then we're going to calculate the probability of getting a chicken. So how do we do this? Well, the simplest way is to just write out all possible arrangements, A, B, and C, right? So we can put 3x in A, and B and C get 0. We can put 3x in box B. We can put 3x in box C. Now we get a chicken. Okay, good news. Also, we can put 2x in A and then 1 and 0 in B and C, or 2, 0, 1. We can also put 2x in B, and then we get 1, 0 in A, or 0, 1 in A, 0, 1 in A and C. Also, we can just put 2x in C, and then 1, 0 in A and B, or 0, 1 in A and B. Over here, we get chicken. And then over here, we get chicken. Finally, we can have 1 egg in each of the 3 boxes and no chicken. All right, so if we count the total number of arrangements, we have 3 here, we have 6 here, we have 1 here, and 3 plus 6 plus 1, we have 10 arrangements. What's the probability of getting chicken? Actually, 3 arrangements out of 10 will result in us getting a chicken. So 30%. It's pretty easy to deal with 3 eggs and 3 boxes, but in the future, when we deal with 1 mole energy quanta being distributed to, let's say, 1 mole is too big. Let's say 50 energy quanta being distributed to 100 vibrational modes or 20 vibrational modes. It's going to be really difficult to draw such a table. So we need a more schematic manner to calculate the number of arrangements that result in the reaction succeeding, and also the total number of arrangements, and then so that we can calculate the probability. So how do we do that? So we'll still use this example, 3 eggs in 3 boxes, but this time I'm going to draw 3 eggs and 3 boxes. All right, first I'm going to draw 3 boxes. All right, A, B, and C. And then I will draw 3 eggs. Well, I can draw 3 eggs on the left-hand side of A. That means 3 eggs in A, right? This corresponds to the first arrangement. So this is my first arrangement here. What about my second arrangement? 3 eggs in B. So when I draw this, I just put the 3 eggs on the left-hand side of B. All right? So that means, okay, if you look at this picture, that means 3 eggs in B. Over here, 3 eggs in A, 3 eggs in B right here. And then number 3. No eggs in A, no eggs in B, but 3 eggs in C. All right? And number 4. 2 eggs in A, 1 egg in B. This is arrangement number 3. This is arrangement number 4. So 2 eggs in A, 1 egg in B, and then no eggs in C. All right? So we can do this. So this is how we draw the 10 arrangements. It turns out that, well, we are looking at the permutation of the positions of the 3 eggs and 2 boxes. Look, if you do not look at C, C is always at the end. So you don't have to look at C. C is always at the end. But then if you look at other pictures, you'll see over here, position 1 is egg. Over here, position 1 is A. Position 1 is A. Position 1 is egg. Position B, egg. Okay, position B, here, egg. Position B, position 2, B. Position 2, egg. So what I'm saying is you are really looking at the permutations of 3 eggs and 2 boxes. All right, so 3 eggs and 2 boxes. You're just putting them in a line. And then we can calculate the number of permutations. All right, 3 eggs and 2 boxes in a line. How many permutations? Again, since we know these eggs are labeled 1, 2, 3, right? 1, 2, 3. So 1, 2, 3. They are distinguishable, right? 3, 2, 1. 2, 1, 3. So even if you have just 3x at the beginning, you may have 1, 2, 3, 3, 2, 1, 2, 3, 1, 2, 1, 3, etc. So you get 6 permutations of the 3x, right? So let's look at all possible permutations. When the eggs are labeled, when the boxes are also labeled, right? So we know there are 3 different eggs, egg 1, 2, 3. We know there are 2 different boxes we need to make arrangements, box A and box B. So 5 distinguishable objects in a line. How many permutations are there? 5 factorial. All right, 5 factorial in total. And then now let's switch the gear. Let's say the 3 eggs are indistinguishable now. You know, if you have like 1, 2, 3, 3, 2, 1, 2, 3, 1, 2, 1, 3, and then 3, 1, 2, and 1, 3, 2, all 6 permutations correspond to the same so-called microstate or the same arrangement. And then we realize that, well, we need to divide this factorial by 3 factorial. All right, so this is the permutation of 3x plus 2 boxes. This is the permutation of 3x. And also, we want to look at the mode C, the most important mode. Okay, only C is the most important vibration mode. If C gets enough energy quanta, the reaction may occur. But, you know, we don't care if A gets 2 quanta or B gets 2 quanta, right? So let's say if, A gets 2 quanta, B gets 0, versus A gets 0, B gets 2. It's the same to us. So I'm going to just say, well, now why don't we just say, well, this B is actually A. I don't care whether it's A or B. A and B are just both A's. So I'm going to have to divide 2 factorial as well. All right, 2 boxes. And now we have the total number of arrangements. 5 factorial over 3 factorial is 5 times 4. And then 2 factorial is 2 times 1. Now we have 10 arrangements. Right? We have 10 arrangements. So if you look at the table here, yes, indeed, we have the 10 arrangements. Now, we're going to have to look at the special arrangements in which C gets 2x or 3x. All right? So if C has to get 2 or 3x, what I will do is I will reserve 2x. Let's say we reserve 2x for C. Now, if we reserve 2x for C, we have only 1 egg and the 3 boxes. Okay? So now we have to distribute only 1 egg into the 3 boxes because 2x are already reserved for C. So now in this case, we'll use the same formula. Okay, we look at 1 egg plus, 2 other boxes because 1 box will have to be placed at the end. So it's going to be 3 factorial. Again, 2x, 1 egg plus 2 boxes. Why 2 boxes? Well, again, 1 box will have to be placed at the end of the line. And then divided by the permutation of 1 egg is 1 factorial. The permutation of 2 eggs is 2 factorial. The result is 3. All right, so we got 2 very important numbers. 10, that's the total number of arrangements. And 3, that's the number of arrangements that has C, box C, containing 2 or more eggs. All right, so 2 very important numbers, 3 and 10, and then 3 over 10, that's 30%. So really, it's just this. If we put 3 eggs into 3 boxes, there's a special box labeled C. When C contains 2 eggs or more, it's going to turn into a chicken. So if we randomly put 3 eggs into the 3 boxes, 30% of chance we'll get a chicken. Let's get back to the chemical problem. If we have 3 energy quanta to be distributed to 3 vibrational modes with the same frequency. Assuming one of the 3 vibrational modes, C. If C gets 2 or more energy quanta, the reaction will occur, and then 30% chance the reaction may occur. 30% chance. All right, this is a very simple numerical example. Now, actually, I want to give you one more example. So in this case, I'm going to increase the number of eggs. Let's say we have 4 eggs in 3 boxes. All right, 4 eggs in 3 boxes. So again, if you are trying to make the table, you're going to see it's going to be more tedious. 0, 4, 0, 0, 0, 4, 3, 1, 0, 3, 0, 1, 1, 3, 0, 0, 3, 1, and then 3x in C, 1, 0, 0, 1, and then we can have 2x here, right? 2x in A, 2x in B, 2x in A, 2x in C, 2x in B, 2x in C. All right, and then we can have 2, 1, 1, right? We can have 2, 1, 1. Right, and then we have a total number of arrangement 3 here. We got 6 here, right? And then we got 3 here, and another 3. So we have now 15 arrangements. More than before, because this time we have more eggs, we have more ways of putting eggs into the boxes. All right, 4 eggs into 3 boxes. And out of this 15 arrangements, let's say over here we get the chicken. Chicken. A total of 6 arrangements will result in us getting a chicken. So 6 over 15, we have 40% chance of getting a chicken. More than before. It's understandable. I mean, we have more eggs. Now it's easier for box C to get 2 eggs or more. 40%. So now let's use the previous formula here, all right? So we're going to put 4 eggs into 3 boxes. Box A, box B, box C, right? And then we put 4 eggs into A. 1, 2, 3, 4 eggs into A. And also we can put 4 eggs into B, right? So this is the first arrangement, second arrangement, first arrangement, second arrangement. So we can keep doing this. So really, we're just looking at the permutation of 4 eggs plus 2 boxes on top. On the bottom, we can divide 4 factorial. That's the permutation of eggs. And we also divide the permutation of 2 boxes. Again, not 3 boxes, because you always need a box at the end. All right, you cannot put an egg at the end because it's unphysical. You have to give the every single egg to a box. And then we can do this simple calculation. 6 factorial over 4 factorial over 2 factorial. 6 factorial over 4 factorial, that's 6 times 5. And then 2 times 1 is 15. A total of 15 arrangements. Let's take a look. 15 arrangements. Again, it's just 4 plus 2 factorial over 4 factorial plus 2 factorial. Oh, I'm sorry. Multiply by 2 factorial, that's 15 arrangements. Okay, now let's reserve 2x for C, for this special vibrational mode C, or the special box C, because once C gets 2x or more, it's going to turn into a chicken. So now we have only 2x left for distribution. Really, you just need to replace this number 4 with 2. All right, so it's just going to be 2 plus 2 factorial over 2 factorial, 2 factorial, and then over on top it's 4 factorial. You get 6. So this 6 arrangements may result in us getting a chicken. So you got this 6 here, you got 15 here, 6 over 15, it's 40%. All right, so if you look at over here on top, when we make the table, we get 15 arrangements. Out of this 15 arrangements, 6 will result in us getting a chicken. Same here, 6 over 15. So really, if we have, let's say, n boxes, n energy quanta, and s vibrational modes, okay, energy quanta are just eggs. Vibration modes are just boxes. All right, so the probability of one of the special vibrational mode, let's say the special vibrational mode, getting at least n double dagger energy quanta. We'll look at the probability of the special vibration mode getting n double dagger. It's an integer as well. This one is integer. Double dagger stand for transition state. But anyway, or activated complex. But anyway, in here we're just use this symbol double dagger. So first we need to know what's the total arrangements. The total arrangements is this. We have n energy quanta plus s minus 1 factorial, right? And then divided by n factorial. Because the n energy quanta are indistinguishable, s minus 1 factorial. This is because we don't really care about, the other s minus 1 vibrational modes. And then on top, we'll have to replace this n with n minus n double dagger. All right, n minus n double dagger. And then plus s minus 1 factorial. Divided by, this is the plus sign. Sorry about my handwriting. On the bottom here, it's n minus n double dagger factorial. All right, so this is the number of permutations of n minus n double dagger eggs. All right, because we have reserved n double dagger eggs for the special box. All right, and then there are s minus 1 boxes. All right, on top, okay, on top, this is the number of arrangements with the special mode getting at least n double dagger h nu or energy quanta. At the bottom, we also put the denominator in the square bracket, and this is the total number of arrangements. Okay, this is a total number of arrangements. All right, so, and then over here, this is indeed the probability of the special vibration mode getting at least n double dagger. So maybe I should put a plus here, energy quanta, and then the reaction may occur. And also, if you pay attention to this formula, you can see we have this factorial, s minus 1 factorial, and s minus 1 factorial cancel. And then on top, we'll have this n minus n double dagger plus s. Oh, I'm sorry about this. Somehow it shifts. Somehow it shifts. So I'm just going to simplify the expression. All right, this stay on top, And this n factorial flips on top as well. And on the bottom, we have n minus n double dagger factorial. We have this n plus s minus 1 factorial. So I'm going to just copy those. All right, this is the essence of the RRK theory. In RRK theory, the probability of the special vibrational mode getting a certain number of energy quanta and results in the reaction proceeding. Okay, that probability can be computed this way. It's n minus n double dagger plus s minus 1 factorial times n factorial. And then divided by two other factorials, n plus s minus 1 factorial and n minus n double dagger factorial. All right, this is the probability. In RRK theory, it's assumed that all vibrational modes have the same vibrational frequency. Well, of course, it's not accurate for real molecules. So in RKM theory, we're going to assume that different vibrational modes may have different vibrational frequencies, and also we'll have to introduce the rotational modes as well to get more accurate prediction in the end.